We began section 4.3 by graphing exponential functions. Now we have the opportunity to graph logarithmic functions. Let's take a look at what the parent functions look like for logarithms. Definition: the logarithmic function with constant base a, where a is greater than 0 and a is not equal to 1, is given by f of x equals log base a of x. Like exponential functions, logarithms have both an increasing and a decreasing variety. That depends on the size of the base. If the base of the logarithm is greater than 1, then we end up with an increasing logarithmic function. If the base is a fraction between 0 and 1, we end up with a decreasing logarithmic function. While our exponential functions had horizontal asymptotes, both of our logarithmic functions will have vertical asymptotes, and each function has 3 key points. Now, to understand where those 3 key points come from, let's compare the logarithmic function to what we've already learned, the exponential function. And remember this key: the logarithmic function is the inverse of an exponential function. So we began by looking at the function f of x equals a to the x. And we discovered 3 key points can be generated by using x equals -1, x equals 0, and x equals 1. When we calculate the corresponding y values, that gives us 3 convenient key points to begin graphing that function. And we observed that that middle key point was always the y-intercept 0, 1, as long as no transformations were present. Our basic exponential function, whether increasing or decreasing, has a horizontal asymptote at y equals 0, which is the x-axis. The domain of an exponential function is always -infinity to infinity, and the range is 0 to infinity. So that's our basic exponential function. Now, if an exponential function is the inverse of a logarithmic function, then we could obtain the logarithmic function by reflecting the exponential function across the line y equals x. So you can see that green curve labeled g of x is the reflection of the exponential curve, the blue curve, across that line y equals x. So the notation for our logarithmic function, as you know, is log base a of x. Notice, if I take the key points of my exponential function and I switch x and y, I end up with the key points for my logarithmic function. The easy way to remember this is, instead of plugging -1, 0, and 1 in for x, we're going to plug -1, 0, and 1 in for y. Do notice that middle point is important? Well, this time it's not a y-intercept, but it is an x-intercept. So our basic logarithmic functions are going to have an x-intercept at 1, 0. Instead of having a horizontal asymptote at y equals 0 like our exponential functions, our logarithmic functions will have a vertical asymptote at x equals 0. Keeping your eye on this green logarithmic curve over here, notice the domain is going to be everything to the right of that vertical asymptote. So the leftmost x value, of course not included on the graph, is 0, and the rightmost x value there is infinity. This time, the range goes from -infinity to infinity. Our lowest y value is -infinity, and our highest y value is infinity. Notice the domain of the exponential function is the range of the logarithmic function, and the range of the exponential function is the domain of the logarithmic function. So remember, the logarithmic function is the inverse of the exponential function. So all of our ordered pairs switch the x and y components, including the y-intercept becoming an x-intercept. Our horizontal asymptote y equals 0 became vertical asymptote x equals 0, and the domain and range switched. If you can remember that relationship, that is incredibly helpful. So let's see if we can graph some basic logarithmic functions. Example 7, we want to complete the table and graph the function including the asymptote and then state the domain and range. So we want to graph the function log base 2 of x. I'm going to rewrite it y equals log base 2 of x. Now, it's much more convenient to choose y values than x values. Okay, if we choose values like 1, 2, 3, log base 2 of 3, log base 2 of 5, those are going to come out to be decimal values. So what I recommend is converting this into exponential form. So I'm going to take the base, raise it to the exponent on the other side, and set it equal to the argument. So this is equivalent to 2 to the y equals x. And then we'll choose convenient y values like -1, 0, and 1. So we're choosing y values this time instead of x values. So if we take -1 and plug it in for y, 2 to the -1 gives us 1/2. So the corresponding x value there would be 1/2. 2 to the 0th is 1, and 2 to the 2nd is 2. So that gives us 3 key points to graph our logarithm. So we have ordered pair 1/2 -1, 1 0, and 2 1. Now before I connect the dots, I want to acknowledge the vertical asymptote there on the y-axis with equation x equals 0. So in this case, we have an increasing logarithmic function. Looks something like this. The domain of this curve would be from 0 to infinity, and the range -infinity to infinity. Let's try another one. We have g of x equals log base 1/2 of x. Again, I'm going to rewrite it y equals log base 1/2 of x. And then we can convert to exponential form. So we could rewrite that 1/2 to the y power equals x. And the purpose of doing that is simply to make it easier to calculate the key points. We'll use y values -1, 0, and 1. So we have 1/2 to the -1 power. Of course, that gives us 2. 1/2 to the 0th power is 1, and 1/2 to the first power is 1/2. So plotting these ordered pairs on our grid, we have ordered pairs 2, -1. There's that familiar x-intercept 1, 0, and 1/2, 1. Don't forget the vertical asymptote. That occurs at x equals 0. And in this case, we have a decreasing logarithmic function. The leftmost x value on this graph bumps right up next to that asymptote at x equals 0, and the rightmost x value is infinity. The lowest y value would be -infinity, and the highest y value is infinity. Now, you know what's coming, right? Once you have a new parent function, you can then execute transformations. So let's give that a try on example 8. Use transformations to graph the logarithmic function. So we're going to approach this very similarly, but we need to start with a parent function. So the parent function for log base 3 of x plus 4 would simply be log base 3 of x. If we convert that into exponential form, we'd have 3 to the y equals x. So I'm going to use this to generate the 3 key points on our parent function. If y is -1, x would be 3 to the -1 or 1/3. If y is 0, x would be 3 to the 0th power or 1. And if y is 1, x would be 3 to the 1st or 3. So those are the 3 key points for our parent function. We have 1/3, -1, 1 0, and 3 1. And before I connect the dots, as usual, I'm going to construct that vertical asymptote at x equals 0. So connecting the dots, we have an increasing exponential function, but remember, that's just the parent function. That's going to be our guide. So that's log base 3 of x. But we want to graph log base 3 of x plus 4. Notice we're adding a number inside the argument. That's a horizontal transformation to the left. So we're going to move our parent function left by 4 points. I'm going to start by moving that vertical asymptote. If we move that vertical asymptote left by 4 units, it's going to end up here at x equals -4. Then we can move all of those original points left 4 units. And connect the dots. We get the same shape and size, but new position. So that would be the graph of f of x equals log base 3 of x plus 4. Now, just looking at that final blue transformed curve, the domain is going to go from the leftmost point, which is bumping up against that vertical asymptote at -4, to the rightmost x value, infinity. And the range will always be -infinity to infinity for your log function. Okay, let's try log base 4 of -x plus 2. We're going to begin by graphing our parent function, which is log base 4 of x. Let's convert that to exponential form. 4 to the yth power equals x. And let's use y values -1, 0, and 1. So 4 to the -1 power is 1/4. 4 to the 0th power is 1. And 4 to the first power is 4. So plotting those points for our parent function, we have 1/4, -1, 1, 0, and 4, 1. Let's go ahead and sketch our vertical asymptote so we don't cross that boundary. Its equation is x equals 0. So here is our parent function, log base 4 of x. Now let's work the transformations in 2 steps on the next one. Notice we have a negative inside the argument. So when we have a negative inside the argument, that's a reflection across the y-axis. So the asymptote is not going to move, but our 3 key points are each going to reflect across the y-axis. So if I take this point and move it to the same distance to the left of the y-axis, our x-intercept moves over here to -1, 0, and our point 4, 1 moves to -4, 1. Notice all the x values are changing sign there. So this would be the graph of y equals log base 4 of -x. But we've got one more transformation to execute. That is, we want to move all of those black points up by 2 units. Notice if we move the vertical asymptote up 2 units, it's not going to change its position. So it can stay put. So let's count up 2 units for each of these points. And connect the dots. Again, they have that same vertical asymptote. So that's our transformed function. G of x equals log base 4 of -x plus 2. So reading the domain of just the blue graph, the leftmost x value is -infinity, and the rightmost goes up to but does not include that asymptote at x equals 0. And the domain is always -infinity to infinity. So the domain will be dependent on the location of that vertical asymptote. But you can also see how to get the domain just by looking at the argument of the function. So let's discuss that briefly. On example A, notice the argument of our logarithmic function was x plus 4. And our domain is -4 to infinity. It must always be the case that the argument of a logarithm is positive. So if the argument of the logarithm has to be positive, then I can set it greater than 0 and solve for x, and observe x has to be greater than -4. Well, that's exactly what we have here in interval notation. Again, the argument of the logarithm must always be positive. On example B, it almost looks like we're violating that definition. But notice if I set the argument -x greater than 0 and then divide both sides by -1, that simply reverses the inequality. So x must be less than 0, and that's exactly what we have described here in interval notation. So that is a brief introduction to exponential and logarithmic functions. The key to understanding their relationship is to remember that they are inverses.